Welcome! In this video, we will be talking about knowledge-based artificial intelligence for the rest of us. Before we do that, however, let's take a step back and talk about artificial intelligence. What is AI? Well, there are many definitions about what AI is and isn't, but essentially, in the field of AI, we want to build systems that exhibit intelligent behavior. Of course, this raises a new question. What is intelligence? What is thinking? According to renowned psychologist Daniel Kahneman, we as humans have two methods of thinking. To introduce these methods, I've prepared a quick experiment. Ready? Let's go. I'm assuming you immediately read the text next to me, even though it explicitly told you not to. This is a nice demonstration of the first way of thinking, which is fast, implicit, and effortless. Your eyes saw the text and your brain simply wanted to interpret it immediately. Let's go to the next experiment. This one might be a bit trickier to do fast. Though you've probably been able to read the equation quickly, solving it will require more work. And this nicely demonstrates the second way of thinking, which is slow and methodical and relies on explicit reasoning. In this case, it relies on the rules of addition in mathematics. Now, in his book, Daniel Kahneman refers to these ways of thinking as System 1 and System 2. System 1 is automatic and effortless and relies on implicit patterns. It is also a black box in the sense that it is difficult to explain why we interpreted something the way that we interpreted it. System 2, on the other hand, is slow and conscious reasoning with explicit information. As System 2 explicitly reasons over rules, it is easier to explain your thinking. Now, why am I saying this? Well, interestingly, in the field of artificial intelligence, we see a similar distinction pop up. On the one hand, there are the data-driven techniques that excel at learning patterns, such as machine learning, deep learning, large language models, etc. On the other hand, there are the knowledge-based systems that rely on explicit reasoning, such as logic-based AI and knowledge representation and reasoning. Interestingly, both these approaches share the benefits and weaknesses of their human counterpart, with the former in general being fast but difficult to explain, and the latter fully explainable but on the slower side. As the title of this presentation indicates, I'll continue talking about logic-based AI. So, how does logic-based AI work? Simply put, starting from knowledge of a problem domain, we will build a formal model so that a computer program can reason over it. This problem knowledge can take many forms, such as handbooks, academic literature, legislation, and much more. Additionally, we'll typically want to involve a domain expert as well to capture their tacit knowledge, or the type of knowledge that they've built up throughout their experiences. As mentioned, the model that we'll be building should be a formal representation. Essentially, we'll want to represent the knowledge in a format that both we and the computer can understand. And this imposes quite a few constraints on the notation, as it should be precise, it should be non-ambiguous, so that the computer can understand it, yet it should be sufficiently expressive so that we can still correctly model all the knowledge of the problem domain. For these reasons, one common notation is first-order logic, which actually forms the basis of many knowledge representation languages. To show an example of first-order logic, let's consider the knowledge of a handyman on hanging up objects on a wall as a small example. Now, this handyman can use three fastener types. They can use nails, which hold up to 10 kilograms, screws up to 25 kilograms, or glue up to 15 kilograms. Crucially, nails and screws both require that they make a hole in the wall. Now, he also knows that there are three wall types, namely tile, brick, or wooden walls, and that we cannot make a hole in tile, because a tile wall might shatter when we make a hole in it. In first-order logic, we could represent this knowledge using the following few formulas. Each group here expresses a piece of the knowledge that was shown on the previous slide. Now, you may notice that first-order logic is perhaps not the most user-friendly format, even for this very small example. Luckily, there are alternatives aimed specifically at non-expert users to essentially enable logic-based AI for the rest of us. In this presentation, we'll be taking a closer look at one such formalism specifically, namely cDMN. cDMN is a table-based notation which extends the already existing decision model and notation standard. This DMN standard is a user-friendly notation for decision logic, where all logic is expressed in decision tables. cDMN extends the expressiveness of this notation to be more suitable for logic-based AI, while still maintaining this user-friendly format of the original. As an example of a decision table, consider the following table deciding a patient's health level based on their BMI. In a decision table, the value of the output variable is defined by the value of the input variables. These variables are shown at the top of the table. In this case, a patient's BMI level, in blue, is decided by their BMI and their waist size, in green. Each row of the table can then roughly be interpreted as an if-then expression. For instance, if the patient's BMI is between 18.5 and 25 and their waist size is smaller than 95 centimeters, they are considered healthy. If their BMI is greater than 25, regardless of their waist size, their BMI level will be derived as obese. Through simple rules such as these, decision tables are able to efficiently represent decision logic. However, one thing that decision tables cannot express are constraints, such as, if you want to go to the army, you must be healthy. For this reason, cDMN extends DMN by adding, among others, constraint tables. As you can see, a constraint table is largely similar to a standard decision table. The main exception here is that the table indicator in the top left corner is now an E star, which indicates a constraint table. Interpreting a constraint table is actually quite easy. For every row for which the inputs match, the output must hold 2. If no inputs match, then no constraint is applied. For this example, this means that if you wish to go to the army, you must be healthy. If not, your BMI level doesn't matter. In this way, we can concisely model constraints. Okay, now let's go back to our handyman example and model the knowledge in cDMN. Let's begin with the fact that each fastening method has a maximum weight. Quite clearly, we can interpret this as the method used imposing a constraint on the weight of the object. So we can model this using a constraint table with the method as input and the max weight as output. Next, we want to decide whether we need to create a hole in the wall, which can be modeled using a simple decision table, like so. Finally, there's a constraint that a tile wall cannot have any holes in it. It is important to use a constraint table here, as demonstrated, as we do not want to make a decision for the other wall types. And there we have it. This completely models our cDMN model for the handyman example. Now you might be wondering, what can we actually do with such a model? Well, cDMN models can be translated for use with off-the-shelf reasoning engines, for instance, the IDPZ3 reasoner. This reasoner also comes with a graphical interface called the Interactive Consultant, which lets us interactively reason over the model. Let's try that. In the Interactive Consultant, you can see all variables of the problem and assign them values. Each time we do so, the system automatically derives the consequences and shows us the result. For instance, if I select a tile wall, the system tells me that I can only use glue, as a hole cannot be made in a tile wall. If instead I selected brick, all 3 methods are still possible. By each time deriving these implied values, the system guides me towards making a correct solution and effectively prevents me from making mistakes. For instance, if I add a weight of 20, the system derives that only screws are possible, which requires making a hole. Besides finding the method based on the weight and the wall type, the Interactive Consultant can also reason in other directions. For instance, if I want to know what the strongest weight is that a glue can handle, I can first select glue and then ask for the maximum possible weight. The Interactive Consultant is also fully explainable, as it can always refer back to the tables it used to get to a conclusion. For instance, in the earlier example of a tile wall, it refers back to the table with the hole constraint and the table which decides if a hole is needed to explain why we need to use glue. Though this is of course a very small example, it already nicely shows some of the possibilities of knowledge-based AI systems. Typical real-life examples of such systems include reasoning over law text, modeling configuration problems, and offering decision support for a wide variety of knowledge-intensive fields. So what are the main takeaways from this video? Firstly, that there are two main AI approaches, namely the data-driven AI and the knowledge-based AI. Second, that this knowledge-based AI typically works by reasoning over formal knowledge bases, which are built to reflect a specific problem domain. In contrast to black boxes, these can fully explain their reasoning by tracing back to the original rules in the knowledge base. Third, knowledge-based AI is not exclusively for computer science majors. Thanks to these accessible methods, anyone can build decision support systems that are trustworthy and explainable. Eager to learn more? Just go to any of these links and get started yourself. Thank you very much for watching.